Now that we have added the functionality to use blueprints for detecting the Oculus Guardian system, it's time to start making something from that data. In the motion controller pawn darts, we will grab a new function that will serve as the dataset for drawing a box in the shape of the player space. Inside of the content folder, characters VR pawn, open up motion controller pawn darts. In the event graph, after the branch we previously created in the toggle Guardian event, right-click and search for Get Play Area Transform. This function will provide us the transform data, the location, rotation, and scale, and to see those individual values, we need to split the transform by right-clicking on the transform output pin and selecting Split Struct Pin. Now that we have access to the data, we need to start drawing a visual. We're going to use a node called Draw Debug Box, which is intended to be used only for development. Before we start creating any more nodes, we want to change the thickness value here. For now, set the value to 2. The draw duration can remain 0 as we will be updating this every frame. Let's quickly move the call to this function from begin play to event tick. Okay, now connect the rotation from the split transform into the rotation of the draw debug function. After rotation, we will scale our box, which will require a little bit of math. The Oculus function will return the scale of this box in meters, so we will need to convert it to centimeter scale to work with the draw debug box. We'll also want to scale the box to fit on the floor. First, click and drag off of the scale node. Releasing the click will allow you to search for a context-sensitive function. The one we are looking for is break vector. This will split the scale vector into 3 floats, x, y, and z. Now we need a new node to create a scale vector. Search in a blank spot in the event graph for a make vector function. Plug x into x and y into y. In the input space on the make vector, leave the z float value as 0. This process is essentially scaling the box in the z space, making it a flat rectangle, rather than a cube or a volume. Finally, we have to take our new vector and multiply it by a float. Pull off the function and search for vector times float. In the space for a float, enter the number 50. This function is multiplying the vector to reach the correct world scale. The reason it's 50 and not 100 is because the scale origin is in the center, so 50 in one direction and 50 in the opposite direction will make 100. Plug the result into the extent input. The last step to drawing our debug in the world is to define the center. The counterintuitive step is to use the player pawn's location rather than the location value from the Get Play Area Transform function. Simply search for Get Actor Location. The behavior of this node is self-explanatory. It finds the world location of the actor, and in this case, it's our pawn. Now, drag off the location vector from this new node and plug it into the center input of the draw debug box. And press compile. Now it's time to test. When you run a level in the VR mode, you should be able to see an outline of your play space on the ground. You will notice that if you teleport, the box will come with you, but could become unaligned. This is happening because of the complex relationship between your real-world play space and the local and world space of your level. I don't need these right now to print to the log or the screen because I've plugged this into the event tick. So press play in VR. Okay, so when I'm looking down and I could see that my play space has been drawn onto the ground, but when I teleport now and I change my direction, there could be occurrences where the play space has now become unaligned with my outer boundary, which has just occurred. All right, so let's take care of that in the next module where we will go about fixing this problem by centering our camera in the player pawn.